Welcome to Malabar College of Engineering and Technology online classes. Today we are going to discuss about torsion, that is coming under mechanics of solids MR 306, that is for Mechatronics engineering, and module 3. Okay. When a shaft is said to be in torsion, when equal and opposite torques are applied to both the ends of the shaft. Actually, this torque means force applied into the distance, perpendicular distance from the shaft. Okay, this torque is equal to P is equal to force into perpendicular distance. Its unit is Newton meter. Okay, force, the unit of force is Newton, and radius means that is a meter. That is Newton meter. Okay. Actually, this torque means that is nothing but a twisting moment acting on the shaft. Actually, this due to this twisting moment causes shear stresses and shear strains on the surface of the shaft. Okay. Then, what are the assumptions of the theory of torsion? The first one is the material of the shaft is uniform throughout. The second one is the twist along the shaft is uniform. The third one is the cross section of the circular shaft is uniform. And the third one is all radii are straight before twist is straight after the twist. Okay. Then we need to derive a derivation of shear stress produced in a circular shaft when subjected to torsion. Okay. For deriving, initially we need to consider a shaft, and one end of shaft is fixed and the other end is free. Then the fixed end is AA and the free end is shown as BD. And to consider any line on the outer surface of the shaft as CD. The length of the shaft is L. Okay. Once the twisting moment, the torque is applied on the shaft, torque is applied on the shaft means there will be a twisting in the clockwise direction of the shaft. Okay. Due to the twisting means the surface, outer surface, there will be a deflection on the point D. Okay. After the twist means the D will be shifted to D dash. That means the line CD will be deflected to CD dash, and the angle of that particular twist is shown as phi, that is on the outer surface. Then on the diagram C means figure C, this is the center or the origin point, that is O. This is the initial point D, and this D will be deflected to D dash through an angle theta, that is the angle of twist. Okay. Now we need to derive what are the various points coming under this topic. Means shear stress, tau is there, then G is the modulus of rigidity, T is the torque applied on the shaft, then phi is equal to shear strain. Shear stress, shear modulus, T is equal to torque, phi is equal to shear strain, that is equal to angle DC D dash, DC D dash, then theta is equal to angle of twist, that is equal to angle D of D dash. Okay. Now the distortion of the point D to D dash. Okay. Distortion that is coming on the surface of the shaft due to this twisting moment. Okay. Then now the distortion at the outer surface of the shaft is equal to distortion at the outer surface of the shaft is equal to d dash. Okay. Therefore, shear strain phi is equal to distortion per unit length. That is equal to d dash per unit length means L. Okay, d dash divided by L. That is equal to actually here the angle means that is tan phi, but tan phi is very small, so we are taking it as phi. Phi is equal to d dash by L. Now consider the diagram C. Consider figure C. Then arc d dash is equal to OD into theta. Arc d dash is equal to OD into theta. That is equal to OD is nothing but the radius of the shaft. This is R. OD into theta. That is equal to R into theta. Therefore, shear strain phi is equal to, substitute the value of d dash in the previous equation, we get d dash by L is equal to r theta by L. Now we have the value of shear strain phi. Then we can directly go to the shear modulus G. What is shear modulus or modulus of rigidity? Therefore, modulus of rigidity G is equal to shear stress at the outer surface of the shaft divided by shear strain at the outer surface of the shaft. That is equal to G is equal to tau divided by phi. That is equal to tau divided by, substitute the value of phi from the previous equation, that is tau divided by r theta divided by L. Or we can write down that is equal to tau into L divided by r theta. G is equal to shear modulus G is equal to tau into L divided by r theta. Or we can write down tau by r is equal to G theta divided by L, or tau is equal to r into G theta divided by L. Okay. From this equation we can easily understand tau, the terms r, G theta and the L. From this term we can easily understand the term shear modulus G, the angle of twist theta and L. All these terms are constants. Okay. Then the shear stress tau is directly proportional to the radius of the shaft r. So we can write down tau is proportional to r, or we can write down tau by r is equal to a constant. Okay. Now small letter q, if q is the shear stress at a radius small letter r, q is the shear stress at a radius small letter r, then we can write down tau by r is equal to small letter q by r. This is equation number 2. This is equation number 1. Okay. This is equation number 1 and this is equation number 2. Tau by r is equal to q by r, and we can write down tau by r is equal to q by r is equal to g theta by l. That is the shear stress produced in a shaft when subjected to torsion. Tau is equal to r g theta divided by L. That is the final equation. Okay. And the next derivation means maximum torque transmitted in a shaft. Okay. Or a solid circular shaft. That will be discussed in the next class. Thank you.